Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. In the depths of space, where gravity reigns supreme and physics pushes the boundaries of possibility, exist objects so dense that a single teaspoon of their material would weigh 6 billion tons on Earth. These are neutron stars, the collapsed cores of massive stars that have undergone one of the universe's most violent transformations. To understand these cosmic enigmas, we must first journey into the heart of stellar death itself. When a star at least 8 times more massive than our Sun exhausts its nuclear fuel, it faces an inevitable and catastrophic fate. For millions of years, the star has maintained a delicate balance between the outward pressure of nuclear fusion and the inward pull of its own gravity. But when the fusion furnace finally dies, gravity wins decisively. The star's core, composed primarily of iron, the stellar equivalent of nuclear ash, can no longer support itself against the crushing weight of the outer layers. What happens next occurs in less than a second, yet it reshapes matter in ways that seem to violate our everyday understanding of physics. The core collapses with such incredible force that protons and electrons are literally crushed together, forming neutrons in a process called neutronization. The core's diameter shrinks from roughly 3,000 miles to just 12 miles, while retaining nearly all of its original mass. This compression is so extreme that if Earth underwent the same transformation, it would be compressed to the size of Manhattan. The collapse doesn't stop gently. When the neutron-rich core reaches nuclear density, approximately 100 million tons per cubic centimeter, it suddenly becomes incompressible like a cosmic brick wall. The infalling outer layers slam into this neutron core at speeds exceeding 30,000 miles per second, creating a shockwave that reverberates outward through the dying star. This shockwave, energized by neutrinos streaming from the core, tears through the star's outer layers and launches them into space in what astronomers call a core collapse supernova. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. The energy released in this stellar death is almost incomprehensible. In just 10 seconds, a core collapse supernova releases more energy than our Sun will produce in its entire 10 billion-year lifetime. Most of this energy, 99%, is carried away by nearly massless particles called neutrinos, which stream through matter as if it barely exists. The remaining 1% powers the explosive fireworks that can outshine an entire galaxy of 100 billion stars. But the true marvel lies in what remains, the neutron star itself. Born from this cosmic violence, these objects represent matter in its most exotic state outside of black holes. Their surfaces are solid crystal lattices of atomic nuclei, while their interiors contain matter compressed beyond anything achievable in terrestrial laboratories. The magnetic fields generated by these spinning neutron stars can be 1 trillion times stronger than Earth's magnetic field, creating conditions so extreme that atoms themselves are stretched into elongated shapes. These stellar remnants challenge our understanding of physics at every scale. They are simultaneously the smallest and densest stars in the universe, objects where a cubic centimeter contains as much mass as Mount Everest. Their existence pushes the fundamental forces of nature to their limits, creating natural laboratories, where we can study physics under conditions impossible to replicate anywhere else. As we'll discover, neutron stars are not just the corpses of dead stars. They are cosmic engines that continue to shape the universe long after their violent birth. To comprehend the true nature of neutron stars, we must dissect these cosmic objects layer by layer, each region revealing physics more extreme than the last. From their crystalline surfaces to their mysterious cores, neutron stars represent a hierarchy of density that defies conventional understanding of matter and pushes the boundaries of known physics. The journey begins at the neutron star's surface, where conditions are already beyond terrestrial comprehension. The surface gravity is 200 billion times stronger than Earth's, meaning that an object dropped from just 1 centimeter above the surface would impact with the force of a nuclear bomb. The surface itself is not the familiar mix of elements we know on Earth, but rather a solid crust composed of atomic nuclei arranged in perfect crystalline structures. These nuclei, stripped of most of their electrons by the intense pressure, form what physicists call a nuclear pasta, regions where matter takes on shapes resembling spaghetti, lasagna, and other pasta-like configurations. Beneath this exotic crust lies the outer core, where matter exists in a state unknown anywhere else in the universe. Here, the density reaches 400 million tons per cubic centimeter, twice as dense as an atomic nucleus. At these crushing pressures, individual atomic nuclei dissolve, and their constituent protons and neutrons flow freely in what physicists call a superfluid. This neutron superfluid exhibits properties that seem to violate everyday physics. It flows without friction, climbs walls, and rotates in quantized vortices that thread through the star like cosmic tornadoes. The neutrons in this superfluid are not alone. They coexist with a small population of protons and electrons that form their own superconducting fluid. This superconductor carries electrical currents without resistance, creating the neutron star's incredible magnetic fields. These fields, anchored in the superconducting core, can maintain their strength for millions of years, creating magnetic environments 1 trillion times more powerful than anything achievable on Earth. As we descend deeper into the neutron star's interior, we encounter the inner core, a region where our understanding of physics becomes increasingly uncertain. Here, at densities exceeding 1 billion tons per cubic centimeter, matter may undergo phase transitions that create entirely new states of existence. Theoretical physicists propose that at these extreme densities, neutrons themselves may break apart, releasing their constituent quarks to form what's called quark matter. In this phase, the building blocks of protons and neutrons, up quarks and down quarks, flow freely, potentially joined by strange quarks to create a form of matter that has never existed since the first microseconds after the Big Bang. The transition from neutron matter to quark matter represents one of the greatest unsolved mysteries in modern physics. Some theories suggest this transition occurs gradually, while others propose it happens suddenly, creating a sharp boundary between the neutron fluid and the quark core. The exact nature of this transition affects everything from the neutron star's size to its rotational properties, making it a crucial piece of the cosmic puzzle. Even more exotic possibilities emerge at the very center of the most massive neutron stars. Hyperon matter, particles containing strange quarks, might form under these extreme conditions. Kaon condensates, pion condensates, and other exotic particle states predicted by quantum chromodynamics could exist in these cosmic laboratories. Each of these phases would create distinct signatures in the neutron star's behavior, from its cooling rate to its response to external perturbations. The structure of neutron stars also varies with their mass. Less massive neutron stars might have smaller cores with more conventional neutron superfluids, while the most massive ones, approaching the theoretical limit before collapsing into black holes, might harbor the most exotic matter states. This mass-dependent structure creates a cosmic hierarchy, where each neutron star serves as a unique experiment in extreme physics, testing our theories about matter under conditions that will never be replicated in terrestrial laboratories. In 1967, graduate student Jocelyn Bell Burnell was analyzing radio telescope data when she noticed something extraordinary: regular pulses of radio waves arriving from deep space with clockwork precision. These signals, initially dubbed little green men due to their artificial seeming regularity, would revolutionize our understanding of neutron stars and transform them from theoretical curiosities into observable cosmic lighthouses known as pulsars. Pulsars are rapidly rotating neutron stars that emit beams of electromagnetic radiation from their magnetic poles. As these stars spin, their radiation beams sweep across space like cosmic lighthouse beams. When Earth lies in the path of these beams, we detect regular pulses of radiation with periods ranging from milliseconds to several seconds. The most precise pulsars keep time more accurately than the world's best atomic clocks, with some maintaining their rhythm to within 1 part in 10 to the 15th power over years of observation. The physics behind pulsar emission involves magnetic fields of unimaginable strength. Neutron stars possess magnetic fields typically 1 trillion times stronger than Earth's, concentrated into a sphere just 12 miles across. These magnetic fields, generated by superconducting currents in the neutron star's core, channel charged particles along magnetic field lines toward the magnetic poles. As these particles accelerate to nearly the speed of light, they emit intense radiation across the electromagnetic spectrum, from radio waves to gamma rays. The emission mechanism operates through a process called magnetic reconnection and particle acceleration in the neutron star's magnetosphere, the region where the magnetic field dominates over the star's gravity. Electrons and positrons are accelerated to extreme energies in the intense electric fields generated by the rotating magnetosphere. These particles then emit radiation through synchrotron and curvature radiation processes, creating the characteristic beams that make pulsars visible across vast cosmic distances. Different pulsars exhibit remarkably diverse behaviors. Young pulsars, recently born from supernova explosions, spin rapidly and emit powerful radiation across all wavelengths. The Crab pulsar, born in the supernova observed by Chinese astronomers in 1054 AD, rotates 30 times per second and radiates energy equivalent to 100,000 suns. As pulsars age, they gradually slow down. Their magnetic fields weaken and their emission becomes less intense, eventually causing them to turn off and become invisible to our telescopes. At the other extreme are millisecond pulsars, ancient neutron stars that have been spun up to incredible rotation rates through mass transfer from companion stars. These cosmic recycled pulsars rotate hundreds of times per second, with the fastest known pulsar, PSRJ 1748-2446 AD, spinning at 716 times per second. At these rotation rates, the neutron star's equator moves at roughly 24% the speed of light, testing the limits of how fast matter can rotate before being torn apart by centrifugal forces. The study of pulsars has yielded profound insights into fundamental physics. Timing observations of binary pulsars, neutron stars orbiting other stars or neutron stars, have provided the most stringent tests of Einstein's general theory of relativity. The orbital decay of binary pulsar systems, caused by energy loss through gravitational wave emission, matches Einstein's predictions with extraordinary precision, earning Russell Hulse and Joseph Taylor the 1993 Nobel Prize in Physics. More recently, pulsar timing arrays have emerged as gravitational wave detectors on cosmic scales. By precisely monitoring the arrival times of pulses from multiple pulsars across the galaxy, astronomers can detect the subtle distortions in spacetime caused by gravitational waves from supermassive black hole mergers occurring billions of light-years away. These pulsar timing arrays complement ground-based gravitational wave detectors, opening new windows into the universe's most energetic events. The precision of pulsar timing has also made these objects invaluable for testing fundamental physics, from quantum mechanics to theories of modified gravity. Some pulsars serve as cosmic clocks so precise that they could detect variations in fundamental constants or the existence of dark matter particles through their gravitational effects on pulsar timing. On August 17, 2017, humanity witnessed one of the most spectacular events in the universe: the collision of two neutron stars detected simultaneously through gravitational waves and electromagnetic radiation. This cosmic collision, designated GW 170817, marked the beginning of multi-messenger astronomy and revealed neutron star mergers as the primary factories for the universe's heaviest elements. The story begins with binary neutron star systems, two neutron stars locked in orbital dance, gradually spiraling inward due to energy loss through gravitational wave emission. Over millions of years, these systems shrink from orbital separations of thousands of miles to just hundreds of miles, with the neutron stars completing orbits in mere minutes. As they approach their final dance, the orbital frequency increases dramatically, and the gravitational wave emission intensifies exponentially. In the final moments before merger, the neutron stars orbit each other hundreds of times per second, reaching orbital velocities of 60,000 miles per second, 20% the speed of light. The gravitational waves generated during this inspiral phase carry away enormous amounts of energy, equivalent to the mass energy of several suns converted entirely into gravitational radiation. These waves ripple outward through space-time itself, carrying information about the neutron star's masses, spins, and internal structure. The collision itself is a cataclysm of unimaginable violence. When the neutron stars finally touch, tidal forces tear apart their outer layers, ejecting neutron-rich matter into space at speeds exceeding 10,000 miles per second. The collision creates a brief, incredibly hot and dense environment where temperatures reach 100 billion degrees Celsius, hot enough to forge elements heavier than iron through rapid neutron capture, a process called R-process nucleosynthesis. During R-process nucleosynthesis, atomic nuclei capture neutrons faster than they can decay, building up extremely neutron-rich isotopes that subsequently decay into stable heavy elements. This process, occurring in just seconds, creates approximately half the elements heavier than iron in the periodic table, including gold, platinum, uranium, and rare earth elements. A single neutron star merger can produce Earth masses of gold and platinum, more precious metals than exist in Earth's entire crust. The aftermath of the collision creates multiple observable phenomena. The merger itself may form either a massive neutron star or collapse directly into a black hole, depending on the total mass of the system. The ejected matter, now rich in radioactive heavy elements, glows with thermal radiation as the unstable isotopes decay. This glow, called a kilonova, can outshine an entire galaxy for weeks, providing a beacon visible across cosmic distances. The kilonova's light curve and spectrum encode information about the merger's physics and the elements produced. Early observations show blue light from the decay of light R-process elements, while later observations reveal redder light from heavier elements like lanthanides and actinides. These observations have confirmed theoretical predictions about R-process nucleosynthesis and revealed neutron star mergers as the primary source of elements like gold and platinum in the universe. Gravitational wave observations provide complementary information about the merger's physics. The gravitational wave signal encodes details about the neutron star's masses, spins, and internal structure through their tidal deformability, how easily they are distorted by each other's gravity. These measurements constrain the equation of state of neutron star matter, providing insights into the behavior of matter at nuclear densities. The detection of GW170817 required a global network of gravitational wave detectors, including the two LIGO observatories in the United States and the Virgo detector in Italy. The time delay between detections at different sites allowed astronomers to triangulate the source's position, enabling rapid follow-up observations with conventional telescopes. Within hours, dozens of telescopes worldwide were observing the kilonova, creating the most comprehensive multi-wavelength study of any astrophysical event. Future observations promise even more detailed insights into neutron star mergers. Next-generation gravitational wave detectors will detect mergers at greater distances and with higher precision, while advanced space-based observatories will study kilonovae across the electromagnetic spectrum. These observations will continue, refining our understanding of neutron star physics and the cosmic origins of heavy elements. Neutron stars represent the universe's most extreme physics laboratories, where conditions exist that can never be replicated on Earth or in any human-built facility. These cosmic laboratories offer unique insights into fundamental physics, from quantum mechanics operating on stellar scales to the behavior of matter, under conditions that approach the theoretical limits of stability. As our observational capabilities advance, neutron stars continue to surprise us and challenge our understanding of the universe itself. The extreme conditions within neutron stars create natural experiments in physics that push every known theory to its limits. The matter densities in neutron star cores exceed nuclear density, creating conditions where our understanding of the strong nuclear force, one of the four fundamental forces of nature, faces its ultimate test. Quantum chromodynamics, the theory, describing how quarks and gluons interact, predicts exotic phases of matter that may exist only in neutron star cores. These include color superconductivity, where quarks form Cooper pairs similar to electrons in conventional superconductors, and color flavor locking, where different quark types become correlated in complex ways. The study of neutron star cooling provides insights into particle physics beyond the standard model. Neutron stars cool through neutrino emission, and the cooling rate depends on the exotic particles and interactions present in the core. Observations of neutron star temperatures across different ages can reveal the presence of hypothetical particles, like axions or dark matter particles, that might interact with neutron star matter. Some neutron stars cool faster than predicted by standard physics, suggesting the existence of exotic cooling mechanisms or new particles. Neutron star magnetospheres create conditions where quantum electrodynamics, the theory of electromagnetic interactions, operates in the strong field regime. In magnetic fields exceeding the quantum critical field strength of 4.4 times 10 to the 13th Gauss, the vacuum itself becomes polarized, affecting photon propagation and particle creation. These effects, predicted by quantum field theory but impossible to study in terrestrial laboratories, can be observed in the emission from highly magnetized neutron stars called magnetars. The precision timing of millisecond pulsars has opened new avenues for testing general relativity and searching for gravitational waves. Pulsar timing arrays, consisting of dozens of precisely timed pulsars across the galaxy, can detect gravitational waves with periods of years to decades. These waves, generated by supermassive black hole binaries in distant galaxies, create correlated timing residuals across the pulsar array. Recent results from pulsar timing array collaborations suggest the detection of a gravitational wave background, opening a new window into the universe's most massive objects. Neutron stars also serve as cosmic laboratories for studying matter under extreme rotation. The fastest spinning neutron stars approach the theoretical breakup limit, where centrifugal forces balance gravitational attraction. These rapid rotators test our understanding of neutron star structure and the maximum rotation rates possible for stable stellar objects. Future observations may discover neutron stars spinning even faster, potentially revealing new physics about the equation of state of ultra-dense matter. The role of neutron stars in cosmic evolution extends far beyond their individual properties. As the sources of our process elements, neutron star mergers have shaped the chemical evolution of the universe, determining the abundance of heavy elements available for planet formation. The timing and frequency of neutron star mergers influence when and where terrestrial planets with sufficient heavy elements for technological civilizations can form. Understanding neutron star merger rates and their element production helps us understand our cosmic origins and the likelihood of finding life elsewhere in the universe. Future observations promise revolutionary discoveries about neutron star physics. Next-generation radio telescopes like the Square Kilometre Array will discover thousands of new pulsars, including potential exotic objects like quark stars or strange stars. X-ray observatories will study neutron star surfaces and magnetospheres with unprecedented precision, revealing details about magnetic field structure and emission mechanisms. Gravitational wave astronomy will continue expanding our ability to study neutron star mergers and their aftermath. Perhaps most intriguingly, neutron stars may hold keys to understanding dark matter and dark energy, the mysterious components that dominate the universe's mass-energy budget. Dark matter particles might accumulate in neutron stars, affecting their properties in observable ways. Neutron star observations might reveal signatures of modified gravity theories proposed as alternatives to dark energy. As we develop more sensitive instruments and theoretical frameworks, neutron stars will continue serving as cosmic laboratories for exploring the fundamental nature of reality itself, ensuring that these dense remnants of stellar death remain at the forefront of 21st century physics and astronomy.